Good afternoon. Questions? Okay. So today we're talking about the double layer model, right? And you may have seen this before. So what's going on? Basically, you have a charge on the particle surface, and you have to compensate for that charge on the particle surface. What you have overall is a bulk ionic concentration, okay? So what that means is that you have ions in solution, and that is always the case. You never have a situation where you don't have ions in solution, even if you have an added salt, right? You have basically H3O plus and OH minus by dissociation of water. You should be familiar with that reaction, right? That creates pluses and minuses, all by itself. If you add acid into the system or base, then you induce a greater charge on the particle surface, either positive or negative. We don't care which direction it goes. In general, the magnitude of the charge is sufficiently large, then the particles repel each other. Okay? And that's the key to electrostatic stabilization. But the problem is that we have to dissipate that charge somehow out of the bulk solution. So basically, if you stick your hand in a bucket of water, you should not get a shock, unless you're not very bright and hanging onto something that is, right, has a potential. So the thing is that we always have an equivalent number of positive and negative charge sites. Even if those charge sites are on the surface of the particle, there's a corresponding charge out in the bulk solution, right, that compensates for that. And the question is how efficiently or inefficiently can we eliminate or dissipate that charge on the particle surface? And that's dictated by the bulk ionic concentration, which is on this diagram here. So what I have is a particle, right? And I don't care which charge the particle is. Let's say it's positive, right? And what I'm going to do is I'm going to bring in ions to compensate for that charge. And ions that are similarly charged will be repulsed or repelled away from that, and ions which are oppositely charged will be pulled in. So what you get is a double layer. And what that means is that at the surface of that particle, you bring in ions, and these ions will stack up at the surface, okay? And they can't stack there very efficiently, but typically what we find is about 3 ion layers thick, that there is, these are strongly held, and those ions are difficult to remove. They can be exchanged. If I change pH, I'll change those ions. But the idea of them being removed is that I'll take this particle and I'll put it in an electric field, okay? Let's say it's positive charge. And what I have is particle in suspension in an electric field, okay? Positive and negative. That particle will move towards the opposite pole, okay? And the velocity that with which that particle moves is dictated by a couple of things. What's one thing? Charge of, okay? So the magnitude of charge on the particle, and also the magnitude of the electric field that it's placed in, right? And there's some other things that contribute to that. For example, if I have a fluid, and I'm in a fluid, right, I get drag, so that slows down the particle, right? You could argue there's also a contribution to the size of the particle, okay? More drag, larger particle, etc. We can correct for that, although typically size goes out of the picture. So what I have is, I have ions that are around this particle, okay? And those ions then get stripped off by the velocity of this particle moving through. And at this surface here, try that properly, I have this layer of ions, about 3 ion layers thick, which is strongly held. And in this movement of this particle, they don't get pulled away. So instead what I have is that layer of ions is fixed. This is called the diffuse layer. And this is called the stern layer. Okay? And the interface between the two is called a shear plane. Okay? So, these get stripped away by the movement of this particle through the fluid. And then it's not the magnitude of the charge on the particle surface, it's the magnitude of the charge at the shear plane. The reason I have that charge is because I'm not able to remove those ions from the surface, and I have a charge at the particle surface. Those ions absorb on the surface. Okay, they essentially stick to the surface. And then I'm only able to compensate for a portion of that charge on the particle surface. And then the magnitude of this potential is called the zeta potential. So, magnitude of the charge on the particle, all right, is then manifested as the magnitude of the charge at the shear plane, and that then is my zeta potential. So if I put it in a higher or greater electric field, then the particle moves with higher velocity. Okay? And if I put it in, if I have greater charge on the particle surface, it moves at a higher velocity. So there's a number of ways of measuring the zeta potential. People really like the zeta potential, but there are some problems. Okay? The problem is that it's not very easy to measure, and it is affected by a number of variables. All right, so where shall we start? How do we get a charge on the particle surface? Okay, I change the pH, and then that drives the reactions that we talked about on Monday, either forwards or backwards. Right? So either goes, if I drop the pH, then I'm increasing H3O plus. I drive the reactions from left or right to left. Excuse me. Put the equations up here. Okay. If I add acid, I drive reactions from right to left. I develop a net positive charge. If I put in base, I drive reactions from left to right, and I develop a net negative charge on the particle surface. Okay. So what I get is the potential at the particle surface. Here is called the Nernst potential. Okay? Nernst potential is the potential that is generated by changing acid or base, changing the level of acid or base in my suspension. Okay? We cannot actually measure that directly. Why not? Why not? Because I have that strongly held layer of ions on the surface that I cannot remove. Right? Now I can titrate and back calculate what that potential is, but I can't measure it directly. So to measure the potential, I then get the potential at the shear plane, which is the zeta potential. What's the potential out here? Outside of the double layer. 0. Right? Because then I'm back in my bulk ionics, I have my bulk ionic strength, I have the concentration of ions in solution, and that always adds to 0. Equivalent number of positive and negative ions. Okay. So, what we do here is that we have what's called a DLVO approximation, which I talked about a little bit. We'll talk about more today. DLVO, Derrigu, Landau, Verwey, and Overbeck. Okay, 2 groups of scientists in 2 locations at the same time came up with the same idea. First 2 were Russian, the second 2 were Dutch. Turns out the Dutch have a real interest in water. If you're familiar with the Netherlands, there's a good reason for that, right? So they figured out the potential at the particle surface and how that decays out into the bulk solution. So what we have is we have our stern layer of ions around the surface of the particle. And what we have here is I look at the surface of the particle and I look at the charge decay as I move away. So essentially, if I'm looking at the charge decay as I move away from the surface of the particle, right? The charge at the surface of the particle is called the Nernst potential. Then I have a diffuse layer of ions out here, okay? And that dictates my double layer thickness. So this is L. My double layer thickness is the edge of that diffuse layer. This layer is the stern layer, right? Now, the DLV approximation, it's an approximation. We say, well, what I will do is I will take this Nernst potential and I will decay that Nernst potential linearly to the potential at the shear plane. That's the approximation. We assume that that decay is linear. All right? And it actually is drawn linear here, although you can't see it. And then after that, we have an exponential decay. So just like this, out to my bulk, out to the edge of my double layer. Okay? So the potential at the shear plane, which is now represented as this value here, this is the zeta potential. So this is 0, right? Zeta potential and the Nernst potential. So see a decrease in the Nernst potential at the zeta potential because of ions which are specifically held within that the string layer. Okay. So this is essentially my decay function, right? So the Nernst potential is a function of pH. Okay? Nernst potential is a function of pH. I change the acid or base concentration in that suspension, cause reactions to occur on the particle surface. Depending on how I change that pH, I'll develop a net positive or net negative charge. I do not care whether it is net positive or net negative in general. I only start caring about that when I start bringing ions into solution, okay, that can compensate for that charge. So now the question is, what dictates the thickness of the double layer? So here's what dictates that. You have this, okay, and out here somewhere you have bulk ion concentration of ions in the bulk. Okay, so it is a finite value. What will happen is that ions which are similarly charged to the particle surface are repulsed or pushed away. And then the farther away you get, the less repulsion there is, so that decays until eventually you get to your bulk ion concentration. So what happens is ions that are similar to the particle surface, they get pulled in. Okay? Right? And then, so these are counter ions. And we make this designation in this way. And these are coions. The reason to call them counter ions and coions is because we don't actually care what the sign is. We just know that they are oppositely charged, or have an opposite sign to the charge on the particle surface. In this case, the counter ions, because we said the particle is positive, would be anions. But if I were to call them anions, and you don't know the charge on the particle surface, that would be confusing. They are counter ions, they are oppositely charged to the particle surface. And then coions. So what you have here, you would argue that you have no ions at the surface of the particle, okay, which are similarly charged to the particle surface. So you could argue that this is essentially 0. Okay? And then you would segregate charge as you move into that diffuse layer to allow ions which are oppositely charged to be pulled to the particle surface and ions which are similarly charged to be pushed away. So we have this decay function for ions at the surface, and where that gets back to the bulk ionic concentration, wherever that segregation ends, is the thickness of our double layer. Good with that? This is called L, double layer thickness, which is 1 over kappa, which is a dihuncal length, or the dihuncal parameter. And that is a function of, what is that a function of? pH. No, this is a function of pH. But thank you for saying that. We assume that the pH doesn't actually change the bulk concentration of ions. Changing pH, fair enough. It's an approximation, not quite correct. Good place to start. What does dictate that? Well, you don't have your glasses.
Yeah. Oh, okay.
Oh, you have them. You just don't wear them. Concentration of ions in the bulk. Oh, now you have your glasses. Does it change your answer?
Yeah.
Okay, good. All right, so the thickness of the double layer, okay, is a function of the bulk ionic concentration. That's actually not quite correct, is it? No. Kappa is a function of the double layer of bulk ionic concentration, 1 over L. As the concentration of ions increases, double layer thickness gets smaller. All right? So they are proportional to kappa, the Bi-Huckel parameter, and that is directly related, the Bi-Huckel parameter is directly related to the concentration of ions in the bulk solution. If I increase the concentration of ions, I compress the double layer. So let's do that. I increase the concentration of ions in solution, then do it now in blue, okay? And I see then the decay function gets faster. My double layer thickness then does this. Good. So that means that what happens to my Nernst potential then? What happens to the Nernst potential?
Nothing.
Good. Why not?
Because we're not affecting the Nernst potential by changing the ions.
That's a circular argument for you.
The potential is dependent on the pH.
On the pH. I didn't change the pH, I just changed the concentration of ions. Right? How do you change the concentration of ions without changing pH? Good question. How do you change the concentration of ions without changing pH? Guess. How would you do it?
Add more particles.
Add more salt. This is all independent of the number of particles in the system, so that's good too. You add salt, right? If I bring in, say, increase the concentration of sodium chloride, I bring in +1 sodium and a -1 chlorine, no change in pH. Okay? It's very easy to demonstrate that. Go in the lab, get a pH meter, put water in a beaker of water, add salt. Nothing should happen with pH. Change the ionic concentration, increase the conductivity of the water, or the resistance of the water. It will not change the pH. Okay? Now what happens is that means the Nernst potential stays the same. What happens to my Stern layer? Say again.
That should also stay the same.
It stays the same, right? It's just 3 ion layers absorbed on the surface of the particle. So this stays the same. Okay? So, but my decay now ends here. So my decay decreases. So what you get is a decrease in the zeta potential by increasing the bulk ionic concentration. If I increase the concentration of ions, I compress the double layer, okay? And when that happens, my zeta potential decreases because I am able to compensate for the charge on the particle surface in a shorter distance. And if I bring in a sufficiently high concentration of ions, I can basically stop all of the repulsion character in the particle and the system will coagulate. So, increase the concentration of ions, I increase the Bi-Huckel parameter, that decreases then double layer thickness. So that means that we have zeta potential as a function of 2 things. Zeta potential is a function of, give me one. Okay, and from that we get the Nernst potential. And the second is
Ion concentration.
ion concentration, and that gives us the Bi-Huckel parameter. Okay, so you could look at it this way, a function of pH and concentration of ions in the bulk. Good? So the zeta potential is a function of both of these things. That can be complicated in this way. Make up a suspension, okay, and change the pH, and then you measure the zeta potential, But when you change the pH, you are corroding the surface of the particle, right? So now you are creating charge on the particle surface. You are potentially dissolving the surface of the particle. That can change your ionic strength. If you add acid into the system and you want a pH of 4, and you measure it goes to a pH of 3, so you add a little sodium hydroxide, pull that back up to 4. Now you are increasing your bulk ionic concentration because you've added sodium from the sodium hydroxide. You've added chlorine from the hydrochloric acid, right? So this measurement is very sensitive to both of these things, pH and bulk ionic concentration. That makes it difficult to use as a process control tool because it's difficult to separate these two items in terms of their impact on the double layer thickness and then the charge, magnitude, and magnetic repulsion in the particles. Okay? People like zeta potential, but it's a pain to measure. Okay? There's a couple ways to measure it, and we may talk about that in a minute. So, I increase the bulk ionic concentration, and that causes then compression of the double layer. It gets smaller. That means I'm able to decay the charge away from the particle surface down to 0 in a shorter distance. That means my zeta potential decreases. What happens if I, say, change the pH? Okay, so I have this situation. Let's say I stay with condition blue. Okay, so I have my increased bulk ionic concentration, and I'm going to change the pH. How would you like to change the pH? All right, so what is my pH going to be in reference to? The point of 0 charge, right? I'm either going to shift the pH towards the point of 0 charge or away from the point of 0 charge. If I am already below the point, let's say, would you say decrease the pH? So if I'm already below the point of 0 charge in terms of pH, and I decrease the pH, then my Nernst potential increases. Okay? As I move farther away from the point of 0 charge, my Nernst potential increases. If I increase the pH and I'm moving away from the point of 0 charge, my Nernst potential will increase. So the way that you should approach that question is in reference to the point of 0 charge. So if you increase the pH or move the pH farther away from the point of 0 charge, is the proper way to say that, okay, then you will increase the magnitude of the Nernst potential. Is that the direction you would like to go, or would you like to go the other direction?
That direction.
That direction. So what does that mean? Yes, you do. So you're going to move the pH farther away from the point of 0 charge, right? What does that do to the Nernst potential? Increases it. Can you draw that on the board for me?
That's better.
Active learning. Now you're all really invested. It's like, oh my God, he's going to call on me next. Maybe.
Hopefully.
You want to tag a friend? Or someone who won't be your friend in a half an hour? All right, I'll make it easy. First, draw the Nernst potential. Identify the Nernst potential. On the diagram I've already drawn, is that okay? We use the same diagram? That's good. You just move the pH farther away from the point of 0 charge. How does the Nernst potential change?
Doesn't change.
No, it does. You just told me it did.
got it.
Can someone remind him what he said?
Yeah.
Okay, so it went up. So pick a point. Good. Can I have my chalk back?
Yeah.
Do you want to stay up here?
I don't really.
Okay. What's my next question?
Obviously, zeta potential.
Who's next? Who wants to draw the decay curve? Don't be shy. Heidi. One of 3. No, it's because you looked away.
So the zeta potential happens.
Not the zeta potential. We want to draw the decay function for the Nernst potential.
So go from this point.
Goes from that point
Or no.
to where? Well, Show me where it terminates. Say again.
We're using blue, right?
No, we're on pink now.
Well,
Well, you're using blue, right.
yeah.
So, okay, identify where it terminates.
Well, it's either a blue or white, right?
But it is here.
Here?
The decay function goes all the way to 0.
Okay.
Does that make sense to everybody? It's going to terminate, go ahead, just throw the dot there. Nope, throw the dot first. There. Nope, at the line. So it goes to 0. This is 0 potential, step aside just a bit. This is zero potential, right? So the decay function will start here and it will end at that point because we're using blue. Right, so we say we didn't change the bulk ionic concentration. All you did was shift the pH. Good? So we'll stay with blue, so it terminates here.
Okay.
Right? Now you can draw the curve. Fair enough. You all get that? Yes, you can applaud. Okay, so, all right. So what we have is, here's the Nernst potential, right? You push the pH farther away from the point of 0 charge. Because my particle is positively charged, which direction did the pH actually change? More acidic or more basic? It does matter. The particle is positively charged. You adjust the pH away from the isoelectric or the point of 0 charge, right? Okay. More acidic. You had it right the first time. I made you doubt yourself. It's not even exam time. Okay. So, who would like to now identify the zeta potential? Can you do it? The zeta potential for the red line. Can you help him out? You got it? So, where is it? Walk him through it.
Where the curve intersects that first curve.
Stern layer. This is the stern layer, right? So it's where the red curve intersects the stern layer. You all see that? Okay, well done. So here's the zeta potential for red. So I move the pH away from the isoelectric point. I increase the Nernst potential. If I don't change the ionic strength, zeta potential goes up. If I increase ionic strength, I compress the double layer, zeta potential decreases. Got it? Okay, I'm going to do another. All right, so what happens if I'm at the point of 0 charge? Okay, it's a straight line, but I still have a stern layer. It's just that the potential at the stern layer is 0, right? At the isoelectric point and the point of 0 charge. They are the same, assuming there's no specific affinity of anion or cation in the system, right? So what I can do is, depending on what I stuff in here, I can specifically change this charge structure. We are not going to worry about that. We are going to assume an indifferent electrolyte, meaning no specific affinity, okay? And we assume that the system is essentially lipophobic, okay? Which means it will not dissolve in water, or whatever our solvent is. Is that good? So this is important. This is technically more correct, all right? Top one is technically more correct. Zeta potential is ultimately a function of pH. It is directly a function of the Nernst potential, okay? And then the second is that it is a function of the Debye-Huckel parameter, okay? The inverse thickness of the double layer, right? So if this gets larger, zeta potential decreases. The Nernst potential gets larger, the zeta potential decreases. Okay, so technically, this is correct, right? And this says the bulk ionic concentration and pH, that's how we change these things, but technically this is more correct, okay? That the zeta potential is a function of the Nernst potential and the Debye-Huckel parameter, right? Let's talk about the Debye-Huckel parameter for just a second, all right? I don't remember the specific equation because I can look it up, right? So kappa is a function of the bulk ionic concentration. That is defined as this. Summation of the square root of C sub I, V sub I squared is kappa. Okay? So what that means is that I'm going to, I do not care about the sign of the charge, because the sign of the charge is squared, or the charge is squared. So if I have -2, it's the equivalent of +2. So it doesn't make any difference what the charge is on the ion that's coming in, positive or negative. The magnitude of that charge makes a difference. Because what I have is then, if I do all this, I'm summation, so I can have concentration of monovalent cations, I have a concentration of divalent cations, okay, I can have the concentration of monovalent anions and divalent anions. I add all those up and I get this value kappa. This approximation of the term in here is a couple terms that have to do with permittivity of free space. There's a 1/pi or something in there. Okay, that bulk ion concentration then dictates what's happening with the double layer thickness. What you see is that it scales linearly with charge. Okay, so if I wanted to pull this out here, it would say charge, but then I have a problem because then it can be positive or negative. Don't care about that. The square root of z squared, okay, scales linearly with the charge. It scales the square root of concentration. So concentration is important, but charge is more important in terms of compression of the double layer. Let's see if I have that. Yeah, pull that up real quick. This is the effect of the concentration on double layer thickness. Okay, this is on a log scale. Does that make sense? Yes. Okay. We're talking about the concentration of ions in the bulk solution, and typically moles per liter. This is 1 millimolar. That's where we typically reside. Then this is double layer thickness. So you see here, Z equals 1, Z equals 2, Z equals 3. This is called the bibuckle approximation, and it requires, for this simplistic view, okay, that my salts are symmetric. Okay, that means that I can look at, say, sodium chloride, or I can look at calcium sulfate, but I cannot look at calcium chloride. Okay, does that make sense? So symmetrical electrolytes means I have a monovalent anion and a monovalent cation, or I have a divalent cation and a divalent anion. The problem with this, calcium chloride, for example, based on this approximation, would be equivalent to sodium sulfate, okay? Because it doesn't distinguish between which charge is where, okay? And they are not the same, they don't behave the same. If my particle is positively charged, then sodium sulfate would be more effective because I bring in a divalent counterion. If my particle is negatively charged, the calcium would be more effective, okay? So you cannot do this approximation for asymmetrical electrolytes. But the picture is clear, right? What I have then is that if I look at, say, a double layer thickness of, say, 10 nanometers, I can calculate the concentration of trivalent ions necessary to coagulate compared to divalent, compared to monovalent. What you should see is that they change significantly, right? The other thing you see is that there's a contribution here of the charge on the particle surface, which is ignored in this approximation, okay? Now, what am I doing? I've got two particles that are attracted to one another because of van der Waals attraction potential, right, which is dictated by what dictates the van der Waals attraction potential between two particles?
particle on the surface?
No,
Oh, the size.
no, well, that's in there. What's the thing that dictates the interaction between the particles? The Hamacher constant. This is like one of those game shows, isn't it? Except there's no prize. All right? So we have the Hamacher constant, right, dictates the magnitude of the charge. Everything we're doing after that is to try to get the particles to repel each other to control dispersion. Now, what we have is, we have this curve, right? If I look at potential, so this is V total, this is V attraction, this is V repulsion, okay, this is DLVO, this is van der Waals, okay? And so I have a Hamacher constant, right? Hamacher constant dictates the magnitude of the attraction potential between the particles. And if I have something like alumina, I have a large Hamacher constant, right? That means the particles are strongly attracted to one another in that fluid. If I have silica, those particles are weakly attracted because the Hamacher constant is small. So the Hamacher constant turns out to be a big deal, and we talked about it on Monday, right? So what I get is a decay function that dictates then the magnitude of the attraction potential between two particles as a function of distance away. So the farther away I get, the lower that attraction would be. Okay? Now what I have here is I have a minimum amount of energy that I need and to overcome that attraction. So in other words, what I want is I'll say, we'll just draw a line here and say, this is 10 kT. Okay, and I need to have at least, if I have less than 10 kT that's attracting those particles together, then they will spontaneously de-agglomerate. Okay? So what this tells me is how far apart my particles need to be in order to not stick together. Does that make sense? So what I'm doing here really is dictating what that double layer thickness would be. In essence, we're looking for this to be L, okay, at least that distance L. And if I can come up with a charge on the particle surface that gives me sufficient magnitude of charge that overcomes that distance, that attraction potential at that distance, my particles will repel each other. So there's a contribution here of the thickness of that double layer. That's how this picks up into the picture, in essence. Okay. Now what I have is on the other side, I have the DLVO approximation. I come up with a curve like this. This is my repulsive potential. Okay? It is dictated by what? Charge on the particle surface, essentially double layer thickness, it all comes in. When I add these two together, I get a total interaction potential that looks like this. Comes off basically like this, comes out. Okay? So this is my primary maximum, if you will. This is my secondary minimum. This is my primary minimum. What I have is I've created this electrostatic cushion between the particles to keep them from agglomerating. Okay? You can do the calculations. They're not trivial, actually. They're a pain to do. I didn't ask you to do it in the homework, did I? I think that's cruel and unusual. Too much work. Okay? So, you get a total interaction potential between the particles. Now, there's an approximation, again, that goes into this. It has to do with that linear decay function. And so what it does is it says, how fast will this decay, will the charge decay as I move away from the particle surface? And so we use that information to calculate whether particles will be repulsive or attractive to one another. And the value that we use to estimate the Nernst potential is the zeta potential. So by measuring the zeta potential, remember I told you that this is linear, that this line is linear. So if I knew this value, I can extrapolate back to what the Nernst potential is. The Nernst potential is actually used in the calculations We obtain that value, though, by calculation from the zeta potential, assuming that linear decay. Okay? So that goes back in, and we can calculate then the magnitude of the DLVO potential between the two. I mentioned Keith DiCarlo, and what he did is he figured out that that estimate of the decay is fine for water, but is incorrect when you get into non-aqueous solvents. And so what would happen is that you're predicting then the shape of this decay curve and how much repulsion you would have between the particles. So let's say I give you a suspension of particles and you wish to disperse that suspension. What do? Change the pH. How do you change the pH? Away from the point of zero charge. Keep that in mind, please. It's a rather amorphous idea, right? We really like this idea of the isoelectric point. We go, oh, I'll go to the isoelectric point, which is the perfect pH to flocculate my suspensions, right? But we can define it, so we like it. Say I have to move it away, the question is how far. So we do this, we look at the behavior of suspensions. We measure the zeta potential value as a function of pH, and I have zeta potential, positive, negative. If I look at alumina, it looks typically like this. Okay? Aluminum oxide. This is a pH of 8.5 to 9.0 is defined as the isoelectric point. So the isoelectric point is where the zeta potential changes sign. Okay? You can say that the isoelectric point is where the zeta potential is 0, but technically that's not quite correct. It is net 0, that's one correction, but it is where the zeta potential changes sign. So where this goes from positive to negative, this is the IEP. If I'm above the IEP, I have a net negative charge. If I'm below the IEP, I have a net positive charge. Okay? Now, you may think that I was sloppy in the way I drew my curve. The curve starts to come down here. The curve comes down because as I increase the concentration of acid, I'm bringing in other ions that are oppositely charged to the particle surface. So if I bring in HCl, for example, I'm increasing the concentration of chlorine ions, and I have a positively charged surface. So I am building up counter ions in that system, and eventually I get to the point where I will start to compress the double layer. When I do that, because of this, okay, I will then start to compress the double layer, and my zeta potential will start to decrease. Now, there is a critical magnitude of zeta potential that is necessary for particles to repel each other. Good? We could say that that is the zeta critical, okay? What dictates the critical zeta potential? What a great question. What dictates the critical zeta potential? Give me one variable that can dictate the critical zeta potential. In other words, what dictates the magnitude of charge that I need to repel two particles? Take a stab at it. Well, that does give me the zeta potential, but what dictates the amount of zeta potential that I need for the two particles to repel each other? Rosemary. The Hamacher constant, very good. Okay, so the Hamacher constant dictates the magnitude of the attraction between the particles. If the Hamacher constant goes up, then the critical zeta potential must go up also, which is an interesting observation. So what happened about 25 years ago, came in and said, oh, we need a critical zeta potential here. They didn't define it this way. They said we need at least 40 millivolts. And that was true for alumina, but it's not true for silica because the Hamacher constant is lower. It's not true for zirconia because the Hamacher constant is greater. All right. So as that Hamacher constant changes, this critical zeta potential value will also increase. Okay. So we would call this zeta critical, right? And that means that I must be below a certain pH value for my suspensions to be dispersed. Okay, and that's how you use this curve. I know that I have to get below some critical value of zeta potential, which we typically do not define. Right? But you would know that as those particles get more strongly attracted to one another, that zeta potential value must get greater for those particles to repel each other. Or conversely, if particles are naturally not very strongly attracted, I don't have to have a very sufficiently large pH or zeta potential in order for them to repel each other. So now, what happens if I increase ionic strength? What happens to the zeta potential? What? Just let's start with a simple question. I have, let's say I'm here. Here's my pH. What value would I like that to be? Okay, 5. Good. Okay, I'm at pH 5, and I increase the concentration of ions. What happens to zeta potential? Increase the concentration of ions. What happens when I increase the concentration of ions? I compress the double layer. I had a student years ago, I would ask a question, and his answer was always compression of the double layer, no matter what the question was. So one day I asked him the question, which the answer was compression of the double layer, and he answered something else. Can't win. So, if I increase the concentration of ions at a given pH, what happens to the zeta potential? It goes down, right? Okay? So if you increase the concentration of ions, right, you compress the double layer. If I increase the concentration of ions, I compress the double layer. Okay? So if I increase the concentration of ions and I compress the double layer, I decrease the zeta potential. In the absence of specific affinity, meaning that I have an indifferent electrolyte, the curve does not shift its isoelectric point of the system, but the zeta potential decreases. This is for an increase in the bulk ionic concentration. Okay, zeta potential will decrease. What I should have done is this, drawn in blue, to match my curve over here. Okay? Had enough?
Yep.
Okay, I believe that the homework assignment covers this material. So I recommend that you take a look. Okay, and I will see you on Friday. We'll pick up more or less here.